Alright, let's get into the programming then. So, Code Warrior is not the place where I'm going to be running the code, or, well, I am going to run it in Code Warrior because it has the full chip simulation. However, I'm going to be typing it inside of Vim. This is due to Code Warrior being absolutely horrid on Linux, mainly because it's probably running through Wine. But that's a story for another day. So let's go ahead and get a basic template out. So this is going to be directly from when you create a starting thing in Code Warrior. And by thing, I mean project. So here we are, and as you can see, it's just the starting file of whatever you want to call it. Of a project in Code Warrior. So here are data definitions, the .data section when you reverse engineer a executable, at least an ELF executable on Linux. So we should think about this in terms of bytes, and 1 byte being 8 bits, and so on and so forth. So the lab states the following, that use ds.w and ds.b, which are not AOBs, which are array of bytes, but rather single definitions. So that means each digit is going to have its own definition. So in this case, we're going to have digit 02, digit 01, and digit, I can't spell the date, excuse me. And we're also going to have a result. So let's go ahead and shift I on that. Do tab twice and do what was the thing? It's ds.b, and we just want 1 for each. Back then they used to populate. Let me see what happened. So am I forgetting my Vim? Okay, so it did what I expected. This time it just was due to my forgetting of the keybinds. However, this is slightly disappointing. Overrode that, whatever. We can fix that with a quick that, right? So we're going to create a byte for digit 1, a byte for digit 2. Well, you get the point. Because I'm counting in from left to right in this case, but I wrote them out as right to left. So this would technically, though, be our, well, let me make a comment first. This would be our 0, this would be our 1, and this would be our 8. I'm going at this live, so there's going to be probably some mistakes, so bear with me. So this is 4, and this is 8 bits, which is equal to 1 byte. Which matches our binary pattern that is given. So 0, 1, 8, or 18 converted to binary is 0001, 0010. So that works out nicely for us. 255 is all ones, or 8 ones. So enough of explaining that. We'll get down into the nitty-gritty details as we come by them. So we now have this stuff. This is a pre-written code. We're going to keep RTS, return to stack. That's all good stuff, I guess. New keyboard, or not new keyboard, just it's a different keyboard than I'm used to. Let's see what we have here. So we know right off the bat, well, let me explain something actually up above. So this is hardware-wise, we have something called accumulators. So the HCS12, I think, is what it's called. I also found the data sheet online. It says Motorola 68 something, or 61 or 60. No, I think it's 68 something. I can't remember exactly. And it refers to these as accumulators, and it's actually interesting that it uses the term accumulators because they are not general purpose registers. They're accumulators in every sense of the bit of they are there for arithmetic and logical operations only, which is cool, but I mean, terminology. Who gets into that specific stuff, right? So let's just make a because I want to explain some of the notation used. So you can see D as a, well, let's just write it out what it is like visually. D, the register, excuse me, is essentially just concatenating A, B, and putting that into one accumulator. And I use the term accumulator here carefully. I wouldn't say D is an accumulator in the sense of A, B. In fact, I would call A an accumulator and B an accumulator extension, and I'll get into the difference of this further down the road. The book, or not the book, the data sheet refers to D as a double accumulator, which is just horrible terminology, in my opinion, because it's not double. I can't see that, or I don't interpret it that way. So the way you should think about this is D is 16 bits. That means you got, and then you got, which in total brings you 8 plus 8, which is 16. So this side is B and this side is A. So right off the bat, you can tell that A is the left and B is the right, which is hence our accumulator extension, because the rightmost bits are the least significant, while the most significant bit is the one on the left, depending on your implementation. For this microprocessor, it is that way. I should just mention that caveat. So that's a really nice thing to know. This lets us get the higher bits or the upper bits of a number, and lets us get the lower bits of a number if we specifically want to work on the lower bits. It's useful, but it's not going to be that useful in this lab. However, our results, our number will be living in accumulator A, due to how we write our code. It could be living in a, well, technically it will also live in accumulator D, but accumulator D is 16 bits, which means it'll concat the garbage of B onto the thing, which is what we don't want. And plus the accumulator D, or double accumulator D, or the special accumulator, it's just not, it's 16 bits, so there'll be extra space for things. Meanwhile, we just want 8 bits, and that's all we care about, really. So let's do another one, a comment on notation. So you have a instruction called LDAA, which stands for and is read as load accumulator A. And you can imagine what, well, might as well. You can imagine what this does. Oops. And I hit the wrong key. but what's its name? Yeah, you can. They're actually meant to be read as that way, and you can imagine what they do. And the one that's really trippy is this, because it doesn't say load accumulator D, right? This is actually read, and this is according to the data sheet. Right? Load double accumulator D. But it's wacko. I don't like this mnemonic. I forget how to pronounce it. But it's what they use, and it's what I'll be saying. Although I will be referring, if I do, to A as the accumulator and B as accumulator extension, just to have that clarified up here in the beginning, because that's how the IBM 1130 did it, and that's what I grew up on. No, but it's what I've done programming for before, and that's the way it's just in my head. For this kind of system, modern ones, x86, it's general purpose registers, and you get rid of that stuff. Okay, so let's go ahead and explain the math. The math is actually really interesting, so I'll do comments like straight to the left, so they jut out. We're going to assign the accumulator extension with the decimal value 48, and that's base 10. Now, why? I would say pause the video and just ponder, maybe do a quick Google search, but I'm going to explain it in a second. And here's why. Consider the following. If you let this symbol refer to the ASCII 0, you should note then is an encoding of 0, but not actually 0. So we have to get the raw value of the ASCII 0. And ASCII has code points. I think they're called code points. I know in Unicode we call them code points. In ASCII they may be referred to something else, but the value for 0, the symbol 0, or the representation of 0 in ASCII is not 0, as 0 is a null terminator. So if you were actually looking at the raw values, or in Java or any other language, if you convert a char to an int that gets it out of ASCII, that gets the raw value that's living inside memory, 0 is the null terminator. It means the string stops there. Meanwhile, actually I should probably clarify, if your strings are 0 terminated, meaning there's C-style strings. There are Pascal strings which deal with that. But the value 0 is generally referred to a null terminator. To get the representation of 0 to an actual physical 0, you have to shift by a constant. It's almost like a Caesar cipher. In fact, you can think of it as a Caesar cipher. So you have what? Let's think. Excuse me. You have encoding of 0. We know, or I think it's written in the lab, that you can do this. Or the symbol for hexadecimal is this in this microprocessor, which is weird, so I'm just going to use this. It's not weird. No Cache GBA also uses the dollar symbol for hexadecimal, but C uses 0x, and that's what we're going to use. So this would actually get us the value of, oh no, it's not 38. Whoops, that's me mixing up decimal. It's this, which equals us raw 0 in machine binary. However, you can also shift instead of by hexadecimal by just raw decimal, which is just 48. And I should mention that it's base 10. So intuitively, humans work with base 10. That because of that, I'm going to at least use 10. I mean, not base 10. I'm going to use base 10 to shift everything. I'm not going to be writing, okay, I'm shifting this by a hexadecimal number, because it just intuitively we do decimal, and that's the one we're most comfortable in, unless you're one of those who believe in base 12, which is, you're an interesting human being at that point. But here we go. A, B. So we're loading the address accumulator extension. Should I do, what is it? Okay, it's not a tab. It's just like 2 spaces. Yeah. So, but we're loading in the decimal value 48 into accumulator B, or the accumulator extension, because the next command we're going to be using will use this to our advantage. It'll subtract. Essentially, we're going to use SBA, which means subtract B from A. So first, well, I should probably comment on this, right? Let's have some code hygiene. ASCII shift constant 0 minus 48. You know, I'm just writing the stuff above it. Maybe, I don't know how. It's awkward to comment and code at the same time. Generally, I do voiceovers, and yeah, well, can't do that now. So 0 is base 10. Righto. Do I want to, well, actually, let me just do something real quick. Yank. Great, now I have a couple of reds, so I can just freely write wherever I want to write. Digit, yeah, let's explain how the digits are working, because I realized that I wrote them in a weird notation, even for myself. Let's just name that digit 02, digit 01, and digit 00, right? 007, bam. So here you're going to have a 0, here you're going to have a 0, and here you're going to have a 0. No, what am I talking about? Go home, you're drunk. I haven't slept in a while, of course. So we have that, right? That's our encoding of the values. I feel like I've written that before. Up above. Oh well, we can ignore it. So let's write out what we're going to do next. We're going to shift digit 2 by our shift constant. Which basically says that, meaning we're decoding it. We're doing the Caesar. We're reversing the Caesar cipher. That's gonna bother me now. Okay, there we go. Nope, too much. There we go. Back to normal. So I had to zoom out so we can fit it. Yeah, it's not. So once we've decoded it from its ASCII encoding, it's going to be a native machine encoding. So once we do the shift, a 0 will actually mean a 0. A 1 will actually be shifted to a 1 in the machine, right? Hardware-wise, it will be considered an actual physical 1, which is useful to us, because that's a lot where our logic's going to actually happen. So before I forget, let's load accumulator A with the ASCII symbol 0. So this is loading the ASCII symbol 0, which is hexadecimal 30. excuse me. Right. So I already talked about, or well, excuse me. I already talked about what I was going to do about with this before, which is I'm going to subtract b from a. So I'm going to subtract the accumulator extension from the accumulator, which is going to result in the result is going to be stored into the accumulator, which is accumulator A. So STAA, which stands for store accumulator A. And we're going to store this in the memory location of digit 2. Not bad. And I'll just make a quick comment. Store result of subtraction into memory. And that's essentially what it does. That's it. That's all we need to do to decode it into native machine stuff. Useful stuff, right? Well, time to repeat this behavior for what we need it for. So we're going to do this for also digit 01 or digit 1. I don't know why I said 01. And we're going to need that for 8, which is digit 0. Right. Wow. Okay. I'm tired. That's wrong. Sorry. So now all the digits are, or the variables, technically the data sections, are, what they're all called. The terminology is just interchangeable, but whatever. There we go. So they're all native machine values that do what we need them to do. So next, what we really need is to propagate what input we got as the input we're interpreting. So propagating. I may be butchering spelling here. The binary pattern with shifting positional placements, right? That seems right. I think I spelled that about right. So just go ahead and load accumulator A, or the accumulator. This is the problem. The terminology is confusing here. The accumulator is A. The accumulator extension is B. And then the special accumulator, or the double accumulator, is just D, which is we explained this before. I'm not going to explain it again. I'm just confusing myself at this point. I'm ashamed of myself. Maybe I'm the only one that has that kind of trouble. Who knows? So we're going to load AB. Not load AB. We're going to load accumulator B. The decimal value of 10. And I'll tell you why in a second. Let's just say, well, I'll tell you right now. Move up 1 placement. So this moving up of 1 placement is actually a really fun thing. I should have probably explained it before rather than later. Well, what? That's awkward. There we go. So essentially, to concat 2 numbers, we can devise a function like such. We'll just call it concat, and the concat function takes 2 parameters, a, b. You know what? Let's even go further. So we'll just call it concat. It takes a type of int, and it returns a type of int, right? That's wrong. That's the wrong type. It takes an int and an int, and returns an int. 2 ints, 2 inputs, and gets you 1 output. So what happens is, let's just say that we have round brackets, which say A, which is the most significant bit, or most significant digit. I should stop referring to digits as bits and whatnot. We times it by 10, right? And we add in B. However, this has a strong caveat. B cannot be 0, and a cannot exceed the values of 0 to 9. Or, yeah, it can't, the digit cannot exceed to 0 to 9. So this is a very flaky function if you think about it. It doesn't have this schematics of what we actually want in a concat function. So I could easily break this by saying, here's 5 and 0. What does that give me? That should give me 500, but it doesn't, because it doesn't work like that. There is actually a way to make it work, which is raising 10 to the log of b plus 1 and something else. It has some fractions. There's a proper one, but it has, again, some domain restrictions. However, this basic one will work for this lab. So that's the type of thing you have to think about. Just how do we go from moving positional placements? In binary, if you just multiply by 2, or if you shift 1, it's exactly like multiplying by 2. Or if you shift 1 to the left, it's exactly like multiplying by 2, which is really useful. So keep that in mind. There's a lot of math tricks to this. So essentially what we're going to do is implement that concat function, not in a subroutine, but just as, straight up magic. Not straight up magic, but straight up math. I don't know why it keeps shortening my spaces. Also, this is a new Vim install. So multiply, we're going to call multiply. Multiply stores the result into the, excuse my language. I mean, not my language, excuse my, wow, dry mouth. Excuse me. What was I saying? Yes, it stores the result into the accumulator extension. So we're going to store the accumulator extension into the value result. Right? Useful. Is it not? We don't need that there. We do need you here. Actually, we need a couple of you. Now that I think about it, okay. So, right, okay. I thought I had did something wrong, but no. We're going to want to multiply by 10 first, and then we're going to want to add. So the next thing is following what this function decrees right here. We exactly just want what it sounds like, which is just magic. Not necessarily. It's, wow. That's so weird. Okay, that should not be doing that, but that's new. That's a new bug. All right, so we've stored result. So now we want to load the result into our accumulator. So this is currently it'll be 0. Then after storing the result, we want to say, hey, we want to take that digit 2. Wait, no, digit 1, because we already did digit 2. We want to take digit 1, and we want to load that into the accumulator extension. And then we want to just simply add that in. So like our concat function, we're just adding it in. So we're going to say add b to a. Now we're going to store the result of that operation, which is datasheet wise, it says ABA stores into the accumulator. So store AA to result. There we go. And I have a space for some odd reason. Okay, so that's done 0 and 1 for our current number that we're thinking about. So now we need to do 2 more operations essentially, which is shifting again the result by 10, so it moves up 1 placement altogether, which would move the number into the hundreds, and then adding in the b, or our remainder value. So to do that, we do a lot of repeat. stuff. Essentially, it's just copying this code again. So we'll yank that. We'll go down here so I don't have to retype and... Okay, I see why now. I have all that mess. Bam. Okay, so this was what? This was after doing digit 1. So, okay. I may have messed up, right? So do I want the... Okay, yeah. I want this. I want to multiply by 10. However, I do not want to do it to... My computer just froze. You've got to be kidding me. Huh. What's going on today, Vim? I have enough memory. Must I kill Vim? Okay. Let's take a quick look what's going on. Mid-time debugging. Okay, clearly that's not working. Can I send a signal that way? Sig didn't do it. Sig term. And I spelled sig term wrong. Sig term didn't do it. Wow. You're kidding me, right? What's going on, Vim? Oh. Vim's gone, but it's still... What? Okay, I just had to clear my terminal. Awkward. Awkward. Just plain awkward. That is embarrassing. Yeah. Recover it. Hopefully. Yeah, it recovered it. Nicely done, Vim. Quite proud of you. Alright. No, I'm not proud of it. Bugs. It's not a nice thing to do when you run into someone else's bug while writing your own code. So, again, we're shifting up the result and restoring it into result. We've explained that. This is just doing the last part, which is just saying, hey, do that to 0, 0, which is great. So this is saying load result, accumulator B, add that to the result, and then store the result into the result. Okay, yeah, that looks good to me. Am I missing anything else? I think that follows our thought path quite nicely. We've explained what you need to do, what this mess of D is. You can load to D directly, so it is technically an accumulator, but not really. It's a special accumulator. What is this now? You got some special space. That's not what I was looking for. There we go. Wow, okay, that was embarrassing. And that's embarrassing as well. I don't know what's up with Vim today. It doesn't do the automatic alignment. It's not been a good day. Can I? Well, you know what? This may be a useless cat, but I'm too lazy to figure it out. So this says just cat out the contents of the file, send it to my clipboard, and whatnot. So now I can come over here because I have the code warrior, and for some reason I have to double click on the file each time I want to type stuff. So I have typed stuff now, and yeah, spacing. Wow. Okay. That's a real disappointment from you, of him. But as you can see, we have the code in here now. We're going to hit simulate or debug or whatever it's called, and it compiles, so that's a good sign. We're going to want these in binary. And we're going to just step over. So we got 0, 1, 8. That's a good sign. Okay, our result currently has 0. Now it has 1. That's a good sign. Now it has 10, so we shifted, which makes sense. Now we've add back our remainder, and that makes sense. And then we have 18, and that matches our binary pattern because our value will be stored into A, and it's 0, 0, 0, 1, 0, 0, 1, 0. That sounds good to me. Let's go ahead and change this 0 to a 2. Okay, now I'm pressing 2, but it's not entering into, so I have to double click here. Frustrating today. Really frustrating. These poor tools. Or I just break everything around me. Welcome to my life. Alright, step over. I'm just gonna rush this guy. So it's following, looks good. Okay, yep, that does make sense. So then it's gonna all switch to ones. And then this is production. Okay, yes. There we go. That looks good. That matches the binary pattern, and it makes sense. So that's nice. So the code works. 255 works, 018 works, and it represents the lab's goals. Actually, I have the lab lying around here somewhere. That's my resume. All right, here's the lab. Yep. The lab confirms that those are the results I should get for 18 and 255. And yeah, so that's 30%. All right. We used ds.b and ds.w only. We did not use the AOBs, array of bytes, mainly because it did not say we could use them, and I wanted to keep it to what was on the sheet. All right, thank you for watching, and have a nice day.